Take a look at the universe. At the largest scales, through our most sophisticated telescopes, things are simple, straightforward. Now, peer into the heart of matter with the Large Hadron Collider. At the tiniest scales, everything aligns. No surprises. It's a strikingly orderly cosmos, from the colossal to the infinitesimal. Scientists thought two grand ideas would explain everything. First, string theory, a massively intricate mathematical framework that, for all its flair, hasn't actually solved any major questions. Second, cosmic inflation, the idea that the universe suddenly expanded faster than light for a fraction of a second. But we don't know what came before, or what powered it. Together, these theories suggest a universe that is super complicated up close and chaotic from a macro perspective. But that doesn't coincide with observations, because the universe is both homogeneous and isotropic. No matter where you are or what direction you look, it's largely the same. So, is this simplicity an illusion? A limitation of what we can see? Or is the universe really as simple and predictable as it looks? If that's true, then the clues to our biggest mysteries might already be hiding in plain sight, waiting for us to connect the dots. But what if the answer lies not in our universe, but in another? Haven't you ever heard of Occam's razor? The simplest explanation is probably the correct one. Suppose astronomers see unexplained lights on another planet. Occam's razor says, don't jump to aliens, consider simpler causes first. Atmospheric conditions, natural phenomena. So, why bring it up here? Many inflation models predict the rapid expansion of the early universe should have created long wavelength gravitational waves, ripples in space-time. Detecting them would confirm inflation. Now, to be clear, we have detected gravitational waves from merging black holes and neutron stars. But the primordial waves from inflation, they're missing. With each new experiment, we rule out more inflation models. While inflation explains why the universe looks so uniform, it introduces new challenges. What energy field powered it? Why did it have such specific initial conditions? Some models even suggest infinite bubble universes, raising profound questions about testability and reality itself. Ignoring Occam's razor here is to assume there are no simpler explanations. And that is something Neil Turok, the Higgs Chair of Theoretical Physics, set out to change. Together with his colleague Latham Boyle, he approached a new model that could answer our cosmic questions, without traditional inflation or string theory. If we use Einstein's general relativity and run the universe backwards in time, we arrive at a single point, the initial singularity. To make sense of this, theorists like Nobel laureate Roger Penrose identified a key symmetry in the laws of light and massless particles: conformal symmetry. It suggests that light doesn't experience the usual shrinking of space at the Big Bang. It bypasses the intense conditions. Imagine a stretchy rubber sheet with a drawing on it. You can pull or squish it, changing the size, but not the shape of the drawing. Conformal symmetry implies the universe could have a similar structure. Turok and Boyle proposed that the initial singularity isn't a one-way origin. It acts like a mirror in time. On one side, time flows forward. On the other, it flows backward. A cosmic reflection. This aligns with CPT symmetry, a fundamental balance in nature. Imagine the universe as a grand stage where particles act out a play. 3 rules govern it: charge, swapping matter for antimatter; parity, flipping the scene as if in a mirror; and time, running the play backward. If you change all three at once, the laws of physics stay perfectly unchanged. A well-rehearsed performance. Yet in our universe, particles dominate over antiparticles, and time flows one way. It seems CPT symmetry is violated. The mirror universe concept reinstates it. It suggests our universe has a reversed mirror counterpart, where time moves backward and antiparticles outnumber particles. This parallel universe may not be a real place, but a mathematical construct to explain symmetry at the origin. Their theory also sheds light on dark matter. We know neutrinos are light particles that spin in a left-handed orientation. But heavy, right-handed neutrinos, predicted to be stable, could be dark matter, interacting only through gravity. Using their mirror hypothesis, Turok and Boyle calculated these right-handed neutrinos could indeed account for dark matter. They predict that if this is true, at least one of the three known light neutrinos must have zero mass. This is now being tested by studying how galaxies and cosmic structures are arranged. The scientists also tackled why the universe is flat and uniform. Using entropy, they discovered that a flat, rapidly expanding universe with a small positive acceleration is the most probable state. And density variations, usually linked to inflation, could be explained through quantum fields. More research is needed, but picturing the Big Bang as a mirror neatly explains features that seem to conflict with basic physics. As the scientist Turok says, "The progress we have made convinces me that in all likelihood there are alternatives to the standard orthodoxy, which has become a straitjacket we need to break out of." What do you guys think? Let me know in the comments. And as always, don't forget to like and subscribe to Brainwave. Until the next time, take care.